Now we dive into the differences between the conventional map and the meta-level sciences physics map, alternative physics map. First change comes over here. We've changed chaos theory into emerging math. There's a lot of different mathematical modalities that are emerging and will continue to emerge ad infinitum. It's just the nature of computation. We continually discover new models. So to just restrict all of this very interesting evolutions in mathematics to just one specific theory, chaos theory, is far too much of a limiter. Emerging math is a much better term. The next change is over in thermodynamics. And there are some severe issues in a number of the modern theories of some of the laws of thermodynamics that didn't exist in the original theories, particularly the concepts of structure and information. Information's evolved greatly in the last few decades. It's no longer information, it's knowledge, reasoning, structure of knowledge, meta-level reasoning. There's a whole change in how we look at what not necessarily information is, but what reasoning is. And that very much is in line with structure. They map to each other. It too evolves. Our concepts of knowledge and reasoning evolve as we learn new computational methods, and that happens in biology also. Because the concepts of structure and information are ever changing, you can't use those concepts along with the concept of entropy in a theory or a law such as thermodynamics. They're ever changing things. So we have to go back to some of the more original concepts in thermodynamics, and then that's more aligned with energy transfer. There was originally one concept of energy within thermodynamics. We're specializing it to energy transfer. Also, what is energy? Particularly from a heat perspective, you have a lot of motions of particles and how they behave from a motion perspective. So it's really macro motion that we're looking at from a heat perspective. And work is also another important concept within thermodynamics. So we've changed what those structures are in the thermodynamics field. We also, over in here, condensed matter physics, we dumped the quantum information. That's really more of a computational tool over in computer science. There may be some physics associated with it, but we really haven't gotten there yet. It's not there. So there's no reason to have that there. We've also changed the entire section over to atomic physics instead of quantum physics, because what's happening is we're really looking at atoms here, particles and atoms. So we're looking at atomic theory, nuclear theory. So all of that's covered in the conventional model that Dominic goes over. The biggest change is we've replaced a whole bunch of things, philosophy, quantum physics, elements of quantum physics, relativity, and the Chasm of Ignorance, and the future. We've replaced all of that stuff that Dominic had, and introduced subparticle physics. Now, there are some subparticle physics models out there, such as string theory, loop gravities. There are a lot of different models out there, and we're none of them have really been successful. They're also a little bit abstract. What we're looking here is more of to stay within the same type of paradigm of particles, interacting particles, that we have with the atoms or within classical physics. So we're looking at an entrained ether. That's basically, we have some medium that's used to create particles, and it's also, that same medium is also what's used to create the behavior of the medium that the particles are operating within. By using these types of properties, there's a whole different set of advantages, and you can see that in some of the earlier meta-level science presentations. What are all the computational, data matching, a whole bunch of different advantages with these types of models. A lot of things emerge. All of the different fields emerge, gravity emerges, electromagnetism emerges, a whole bunch, quantum field, quantum behavior emerges, relativity behavior emerges. So when you start looking at, okay, let's just be restricted to subparticles and come up with a model and how subparticles can behave and interact to create both behavior within the containing medium and also the creation of particles. And there are some successful models from that perspective. So using that perspective and say, okay, let's just go down and say we've got subparticles, we've got an entrained ether, as described. It's just another name for a ether or medium that is connected or integrated with how the particles are behaving. And if the medium makes up both the particles and the behavior of the medium, that you have that's entrained ether. So we're going to look at the 6 different large fields within subparticle physics, and what happens is you can look at a whole bunch of anomalous behaviors and anomalous models that are out there, and they can all be categorized from this perspective. Foundations or philosophy, we've already talked about a bit, and that's meta-level science. So we're with meta-level science, you're no longer in the realm of philosophy. You're really looking at concrete science from a computational perspective, because everything is emerging from lessons learned from working with computational sciences. The next field we look at is particles. Okay, this is a whole subfield, and it basically, how do the subparticles interact to create particles, and what's the behavior of those particles. So there's basically 2 concepts in mathematics that everybody's familiar with. You have the continuous and the discrete. Discrete, ones and zeros, integers. Basically, you get specific numbers, 1, 2, 3, 4, 5. And that's one whole field. Computer science is associated with it. Whenever you implement anything, or actually whenever you do any computation, even if you're doing it by hand, it's always discrete. Continuous is concept, and that's basically you continually get things closer and closer to each other, step by step. And functional analysis, a lot of our calculus, a lot of different modalities we have, that real numbers is all oriented around continuous. But there's actually an emerging third area, and it's basically gradations. Basic way to describe that is that if you I think it's called cymatics, if you basically have a plate, put sand on it, then you put different sounds, you'll have different structures forming. Same thing will happen if you use sound on water flowing out of a tap. Different structures in that flow will form, depending upon the sound that's being played. And each one of those is basically a gradation, sort of like discrete things, but there's play in them. Okay? It's you make a jump, but there's a little bit play. You can have some changes. So that's what we call gradations, and there's a whole field of mathematics that's being used fairly extensively, has been. It basically underlies quantum. Basically, it's probabilistic concepts where you have these gradations, but with quantum theory, you don't have that play. By having a subparticle model where you have these gradations, but you have play within the gradations, you can actually match to and map a lot of phenomena that's out there. So we're going to look at some of the subfields within this, and we're going to play with them a little differently. Some of the more well-known models or fields that people have been putting a lot of time and investigation in, we're going to generalize them to what they're really covering. And then for the lesser-known fields, where very few people are working in the area, we're just going to try and pick out specific named theories or models within that, just to characterize the ideas. Subquantum kinetics is probably the most prominent one, because in essence, it's the foundation for a lot of this concepts within meta-level science, in comparing different physics models. It's an excellent model. Basically, looking at, okay, what type, if we're trying to create a subparticle model, How can we do that in a fluid dynamic system? How can we do that, adding in the reaction and diffusion on top of the fluid dynamic system? So we're trying to use some of the more complex mathematics that has been talked about here, and we're trying to use them to actually create subparticles, to use them to create behaviors of subparticles so we can get particles. And subquantum kinetics goes into that. There's a number of different simulations out there. It's not a heavily investigated field at this point, not too many people in it. However, they do have some very interesting results, and you can actually see the structure of particles not being quite similar. There are actually several different layers in order to get an actual simulation of a particle running, so that you have, the particle might have one external behavior, but within it there's a whole bunch of different sub behaviors and layers of behaviors within it. Torsion fields, Shipov has been working in that area, and what that's really looking at is, okay, we've got the particle, and how is it affecting some of the things immediately around it? How the spin and the spin of things around it. Now, there's sets of equations to do that. It doesn't look at it from a subparticle perspective, but the behaviors that are described by the equations and the behaviors observed in the experiments can all be looked at from a subparticle perspective, and looking at, okay, how are the subparticles behaving. When we talk about unstable particles, particle physics, which is a huge field, it was one of the areas that was in this purple area before that we've sort of moved it out. It's really a subspecialty. You're looking at particles that have almost no lifespan whatsoever. It's like the subparticles are interacting. They try and form something, but it doesn't last for very long. And what's the behavior of that? What are the patterns of the different structures that form? But it's not really looking at what the internal structure is. It's just looking at sort of mathematical, it sort of looks this way. You could say that quark theory's in there, but you don't necessarily need to have that. That's a bit of a hodgepodge of a whole bunch of different mathematical groups that have been patched together. But there is study on what actually happens there. But in essence, all you're really looking at is a whole bunch of different lines drawn on photographic material at an extremely high cost. And these are things that are so unstable. There's questions on any value in that research whatsoever. I think it's much more valuable to look at the breadth and depth of different subparticle models that are out there, and all of the anomalous behaviors that we see out there, and look at all the different new types of models we can create with all the new types of computational tools we have today. Light interactions, there is something happening when you have light interacting with particles. QED, quantum electrodynamics, goes into that as well as other things. This too was QED was one of the things that was talked about here. We've generalized it here because if you look at subparticles, what's the behavior in the medium? Light is moving in the medium, and what's happening there. With the subquantum kinetics model, you see some of the same interactions happening with light in the medium. It's just not forming a particle. It's going in waves in directions, as opposed to wrapping up in circles around it. So this is a whole field of endeavor that can be looked at, not just using one specific computational model, but potentially using other larger models. But again, it's a field within subparticle physics. What's the behavior of the medium interacting with the particles? How does the behavior operate? So that's particles, but then you move on to the next level up, where you have atoms. So atoms are combinations of particles interacting with each other. Give you an example of what you might see from, let's say, the quantum structure, where you see an electron on one side of an atom, then all of a sudden it appears in another pattern on another side. Well, if you look at subparticles reacting with each other to form particles like electrons, so you've got this balance of fluid flows and reactions and diffusions associated with it that create a particle on one side, and then when it unforms, you have to balance on the other side, and a new electron will form, because you've got these balances of all these fluids flowing and reacting with each other and diffusing with each other, and because of the subparticle behavior, you're going to have them forming in different places in the atom. All the particles are going to arise, and you can see that different particles will form one place one time, then another place another time. So this is really looking at how all the different particles form in a combination at the atomic level. To give you an idea of what particles are, think of a particle as a spinning vortex. We know all particles, are spinning. So think of it as a spinning vortex, and again, it's a gradation that the subparticle reactions behave in such a way that you can get this structure forming. And we've actually seen this in chemistry. We've seen this type of gradation of formation when you get the right balance of reactions between the associated elements within it. In this case, it would be subparticles reacting with each other. But we've also seen in chemistry that structures can form. So think of it that we have these structures formed, but then there's also a medium around the structure, sort of like a tornado with stuff around it. So the tornado itself behaves in a specific way, but then there's stuff around it that's affected by that. So if you get two tornadoes next to each other, you can potentially get a third vortex forming it. Or if you get 4 or 5 tornadoes, you can get potentially a fifth or sixth tornado form between them. And that you think of that as you've got all these spinning vortices in space, and they're reacting with each other. That's how the atoms are interacting with each other. With cold fusion, a lot of the work has happened is that you have a certain crystalline structures where you have several atoms that are holding everything together. You throw hydrogen in there, then you throw some heavy duty light or electromagnetic or microwaves in it, and there's lots of observations and lots of research showing that new atoms are forming, new particles. It's not the particles; it's you're getting new atoms that are forming within that space. So that all of this, crystalline, heavy holding of structure, and then you hit it heavy with light. That you're going to have behavior, and you're going to have forming of new structures. So the subfields here is we've got cold fusion or low energy nuclear reactions, LNR. Also, there's a number of different scientists who've come up with new models like vortex physics by Mile, and they're looking at what are the atomic structures, how can they form. They're not necessarily looking at it from a subparticle perspective. They're looking from perhaps more of a functional perspective or scalar wave perspective, but they're looking at how the atom structure, just like with torsion fields, this can correlate with subparticle behavior, subparticle flows. But why we've stuck this in this area, even though we have a section for flows, is because a lot of the focus of the potential vortex or vortex fields or scalar waves, different names for the same thing, is oriented around the forming of atoms and how these waves and patterns can form atoms. Transmutation, again with cold fusion, we're seeing new atoms being created. There's also some researchers who are looking at, there might be potentially alternative states. Just like there's some unstable particles, there might be some alternative states separate from the standard quantum states in atomic theory. And they've looked at some of in that area. So that's basically looking at subparticles, but from an atomic perspective. How does the subparticle behavior affect atoms? Moving to the next level is how can the subparticle behavior affect larger structures, molecules. And there's some very interesting books, one by Claude Swanson on life force, and that a lot of things grow better if you have faster spinning particles or atoms. As you spin things up clockwise, you've got more life. If you spin them counterclockwise, you got more gravity. So the spin can affect how things grow. And this correlates with acupuncture or qi, which is part of traditional Chinese medicine, or prana, which is part of traditional Indian medicine. That there's a lot of different medicines associated with it. That if you have an effect, you get results. There's other researchers. Orgone was something that was done in the 1930s by a scientist, and he was actually persecuted for working in this area. But he was working with materials that, you have a dielectric and a conductor and next to each other, and you can create certain behaviors or energy storage in a centralized area. So what we're looking at here is combinations of particles and how the behavior of subparticles, how that affects the particles and the atoms, whether it be spin or different materials next to each other. We're looking at how that has an effect at the global level. In both cases, we're looking at the effect on life, which is a whole bunch of molecules connected together. Orgone, you have different materials, but it too went into healing aspects. Ormus, same things happening there. We're working, they're seeing a lot of anomalous behavior, including some stuff that suggests some alternative states of molecules in atoms and particles within atoms, and that when you get different chemicals mixed with each other, you get different behaviors. Why we've put this in the material area is because typically the end result is some type of molecular structure. Ormus is usually a combination of molecules together, so that's why we put it over in this area as opposed to the single atom area. HHO, energized water, they've done some very interesting studies from a fourth phase of matter, that with ice you get a crystalline structure that's three-dimensional. With water, it's just a whole bunch of different particles in a liquid moving around, or in a gas moving around. But if you put a liquid next to a material of water, there's actually a two-dimensional lattice that forms next to it, and that two-dimensional lattice copies itself, so that you can get, depending upon the material, with some materials you can get up to 100,000 layers built up, and that it in some sense has a memory of the material that it's next to, because that it can actually be copied outside of from water element to water element. This might have something to do with homeopathy. Energized water, what you're seeing is you're seeing water being spun more quickly. Again, that relates to chi or life force. But here we're looking at water and what are the different structures that can form within water. Again, we're looking at materials, molecules. How does the behavior work? Do you have this? And some of the things with HHO, that's where you. So with the layer of the lattices, the two-dimensional lattices, you don't actually have H2O, you actually have H3O2, and you can literally, because that's going to create a whole bunch of hydrogen ions in the middle of the water, away from the material. You can actually put a little light bulb with one wire next to the wall, not touching it, and one wire in the middle of the water, and you can actually have light flowing because the difference in ions from the H3O2 to the hydrogen ions in the middle. So you're seeing different behaviors, but you're also seeing structures being formed. And some of these structures might be these flat lattices, but they also might be these spun spirals. And that's some of the theories within the HHO field. The HHO field, they're breaking hydrogen oxygen apart using different methods, sound, vibrations, particularly electrical stimulation. But one of the things I think they're seeing that there's a spiral being created, that HHO lattice is forming this very tight spin. And again, that relates to life force or changing the behavior of what's going on with the subparticles. Directed energy, there's a whole bunch of evidence that the government is sort of secret government stuff. Philadelphia experiment, some of the stuff happened at 9/11 potentially, some of the things that we've seen in the Iraqi wars, etc., that we've seen some destructive capabilities, potentially using microwaves or other strong waves. And there's a whole field of research into what actually happened. They were able to observe destruction of capabilities. If that the particles start breaking apart when you put heavy microwaves and mixes of microwaves on things in electrostatic fields. So that when you put all these fields together, it can help break up the particle structures and turn concrete and steel to dust, that type of thing. So it's a field. It's basically looking at how are you affecting the molecular structure of things using the behavior of the containing medium and the particles. Moving on to flows, other fields of research. You have magnetic motors, and this is more of what is exactly the behavior of specific electromagnetic fields. And across a number of these different theories that are out in this alternative physics models, you're seeing that magnetic flow is basically fluid dynamic flow, or electromagnetic flow is really a flow of the subparticles. How do the subparticles actually flow? And since you have a fluid dynamics, while it might match the general equations that are associated with calculus, if you dig deeper into it, that those fluid flows might have numerous gradations and lines within it. Think of putting a whole bunch of iron dust on a piece of paper and then putting a magnet underneath it and bopping it a few times, and you can see that you have all of these lines of magnetism flowing. But it's not a space, it's specific lines, so there are these specific gradations. So people who've been working with magnetic motors have noticed that if you cycle things, you can sort of pull some of the energy. Potentially, it's the magnetic flow that's in the Earth itself that you're pulling out by just lining these things up, so that it's just like dipping in a water wheel. You're dipping something in the flow, then it comes out of the flow. And if you cycle things just right, you can do that, because within the magnetic field you have all these places where it's going strong, and other places there's sort of a gap within it. So you maintain conservation of energy. Actually, if you look at things from a subparticle perspective, you get much better correlation with conservation of energy. The type of conservation of energy you have is very much particle movement is being energy, or in macro, groups of particles moving together. That's what energy is, and that you have that same interpretation and concept built not just at the classical physics level, but you also have it at the atomic level, and you also have it at the subparticle level, so that you have that same concept of conservation of energy across all fields. With the standard conventional model of physics, you have these quantized energy, and it's sort of just a measurement. But if you break it down and say, okay, all this quantum behavior is really subparticle behavior, then you say, okay, we can break everything down and say, oh, great, we've got this same concept of conservation of energy, both at the subparticle and then the atomic, because the quantum are made up of subparticle behavior, all the way up to the classical physics. So it really ties together concepts of conservation of energy. Otherwise, the concepts of conservation of energy vary quite a bit in the different large areas. So you also have electrostatics, and that's basically what's the basic flow of electrons from a static electricity perspective, where you're putting a whole bunch of negative ions, positive ions on one side. Well, here it's not just the ions. You're basically looking at, well, it's a flow of subparticles. You're getting a whole bunch of subparticles on one side, one subparticles on the other side, or a flow, a spinning of the subparticles. So you can enhance the electrostatics field, which is a whole bunch of anomalous behavior in it, by looking at things from the perspective of a subparticle flow. Spin dynamics, a lot of open questions in that area, a lot of different models that people are using. This is where people look at MRIs and have working tools, etc. But the theories and models are not quite where they want it to be. These can be enhanced by looking at things from potential subparticle flow. Electrogravitics, there's a whole bunch of research in this area by alternative physicists, and people have gotten some mild results, but some of the stuff that has had relatively good success, all of a sudden was classified in the 50s, 60s. And there's a great book by Paul Laviolette on that topic. Paul Laviolette is also the founder of subquantum kinetics. Ether concentrations. Okay, so we saw that we replaced particle physics with something more general, as opposed to a specific computational model. We were looking at just the general study. We did the same thing with light interactions. Well, here we're looking at relativity as one specific computational model that talks about a specific set of behaviors, but there are other computational models basically looking at the different entrained ether concentrations affecting behaviors around large gravitational objects. So again, we're generalizing something that's one specific model that's well known. If it's a not well known model, but it gives us a lot of information, we're talking about the specific model, such as subquantum kinetics, SQK. Using subquantum kinetics, there's a whole bunch of astronomical implications. We were talking previously about having particles spinning and potentially creating new particles. That has huge astronomical implications. It means that planets grow. There's a lot of evidence supporting that. Pangaea is the study of how the continents were connected. And one of the things that they never mention about that is, well, if you look at the other sides of the continents, they also connect. So it's as if all the continents were connected and then they all expanded. Well, this is understandable if you have subparticles that are basically spinning vortices and can create vortices between them. So basically the whole cosmological models, galactic formation, planet formations, all of that changes because basically things are growing, stars are growing, planets are growing. You can also look at it from let's say dinosaurs and mammals. You see that right after the dinosaurs disappeared, you have all these mammals that came after them. They were almost as big as the dinosaurs, but then they slowly and surely shrank. Well, if gravity continues to grow, you're going to get that type of behavior. Gravity will grow if you continually have more particles being formed. So that's part of some of the general evidence that most people can recognize and understand, but there's a whole bunch of associated mathematics with it. There's also a number of different alternative physics models where they're looking at ultrafast behavior. Some scientists looking at gravity believe that that's almost instantaneous. Koryzhev was a scientist, and it's not quite the correct pronunciation, but we do talk about it in the earlier meta-level science presentations. He did some research where he blocked out a telescope and measured. He could actually, after blocking out the telescope, put petri dish underneath, and he could actually get responses from the petri dishes when it pointed directly at the sun, even though all the light was completely blocked off. One of the interesting things about it is it wasn't when the light reached the telescope, it was when the telescope was pointed directly at the sun that the behavior was noticed. Basically saying is that it's not, the speed of light takes 8 minutes, so that this behavior was noticed before that, 8 minutes before that, so it was almost instantaneous behavior. So gravity might behave that way, some other waves coming from the sun might behave that way. Or it might be combined quantum entanglement might behave that way, that the speed of light in some of these theories, such as subquantum kinetics, is really the speed of the reactions within the subparticle, and that you can potentially have other flows of that's a specific set of reactions within the subparticles, that there can potentially be other behaviors happening within the subparticles that can be much, much faster and correlate with some of the things that have been observed. But again, in this whole area of research, we're looking at how the particles behave from a flow perspective. This is how the subparticles behave from a flow perspective, both larger molecular structures with flows of the subparticles around them and the behavior of the large groups of particles themselves. Final area is information, and we were talking about the fourth phase of water, where they can see that you can get different structure of of water that basically matches potentially the molecules that was around. So here we're looking at, well, what information can actually be stored within, whether it's water, or what information can be stored within the subparticle structures. And this might be the subparticle structures that are the waves that are around the particles, or other structures around the particles, or within the particles themselves. But for the most part, so we're looking at what information can be stored. There's some very interesting experiments done by Nobel Prize winners back in the 2002, 2003, 2004, that type of timeline, where they put gene forming material in water, and you can't get new genes to form if you just put the material in. Typically, you have to put at least the starting part of the gene in order to get it to completely form. Well, they put this medium. What they did is they took an electromagnetic reading of something that had these genes in it, a medium that had these genes in it, and then they played it back in a completely different country, where they just had the material for the forming of the gene, and the gene formed, even though there was nothing there to tell it. So there was some information stored in the electromagnetic medium that was transmitted. So we know that there's information that can be transmitted within, whether it's electromagnetism, or if you're looking from subparticle perspective, within the subparticle structures. Morphic resonance has gone into gory detail in a lot of different experiments, at looking at what information have we seen, whether it be mice knowing how to learn things easier, or crystals knowing how to learn things easier, or people or other elements of what type of human level information or species level information have we seen that's actually transmitted beyond standard models. And all of this information can be structured. I mean, from a hard concrete physics perspective, it's got to sit somewhere. So we're looking at, well, is it an electromagnetic medium? Is it in some type of medium that moves faster, ultra fast? Where is the information stored? Morphic resonance is looking at what is all the information that we see, how is the information structured, which sort of gets into the computer science field, but it's information, it's in structure, and where is it sitting? Remote viewing, dowsing, there are all these in psi research and traditional research into this type of phenomena, is that there's information that can flow and can have effect on things, and it's got to be sitting somewhere. And so a lot of these fields look at, well, what's the structure of the information that's flowing, particularly dowsing, remote viewing, where they're looking at the structure of it and how can we work with the structures of information. Homeopathy and radionics, this is looking at, well, there's information potentially in this medium, like electromagnetic or sound, and if, or within the water, that there's been some recorded structures, and let's say you put some healing or other medium, or maybe the sickness itself in water, and the water copies it, whether it be within the electromagnetic field of the water, or if it's in the chemical structure of the water. What is the HO or the H2O or H3O2 structure look like? H3, in this particularly the H3O2 structure, look like from a chemical perspective, or is it an electromagnetic field? So what does that structure actually look like? How can it be copied and then transmitted? Because we've taken the chemical out, the bad thing out, or the good thing out that's completely in the water, and the water just had that information, and it's being transmitted to the drinker of that water, and it has provided healing aspects. So again, it's information that's being passed and being utilized. Radionics sort of does the same thing, but it's working more strictly with electromagnetic or scalar waves, some type of waves, some type of waves within the medium, whether it's electromagnetics or sound or light, or some type of form of structure within the subparticles. and that there's information within it. So that's this final area. So I think I've given you a brief intro into some of the concepts or some of the different things being looked at from an alternative physics perspective, and particularly from opening up the concepts. We're looking at, well, what are all the different models that are out there? You want to have a breadth of models, you want to have a breadth of data, you want to try and handle as much anomalous data out there. You don't just say if the data doesn't match your theory that it doesn't exist. And that's ludicrous. Like saying, well, this nut doesn't match my wrench, so the nut doesn't exist. No model can fit everything. No one model rules everything. So thank you for listening, and any questions, feel free to email me or comment.